I'm starting the recording now, so if you are watching this, you can try this FRQ, and then you can see me talk about the rubric. I'm talking to anyone who's not in this class, but watching this at a future time. It is me from the future. Cotangent is one over tan. Should I go tell him supporter of that little football? He'd be upset. He would be pretty upset. I think he might try over here. they'll never give one where it's going to take your calculator like extremely long time. I could see a few seconds. You guys look out. I learned a little info yesterday that's going to make our lives a little easier in today's lesson. We're doing integration and stuff. Did you graph the left side? I was just curious what shows up in the graph. Well, graph this, like y equals that, and then y equals 2, and see what they cross. Yeah, I think you would just want to be in regular Cartesian. Okay, that's a good question. I don't know if those matter. Yep, okay. Definitely works in Cartesian. polar wouldn't make sense, or parametric wouldn't make sense. I think it would have to be in just like a regular function. In fact, I don't think you'll ever want to actually be in those other modes unless you're curious what the actual graph looks like. I don't think you'll ever switch over to parametric or polar. 2 minutes. 2 hours. What do you think, Vincent? Take a shot, huh? Is there a third option?
Yeah, it's either right or it's not.
I know, but you said it.
Yeah, so it's probably right or it's not.
You said it could be right, it could be wrong. It's probably one or the other.
Yeah.
Wouldn't it have to be one or the other? Not probably.
That's my.
Well, it would have to be.
Yeah.
That's
That's what I'm saying. What's the matter with you? That's
So it's a 50-50 chance. You're either right or.
You're either gonna win the Mega Millions tonight, or you're 50% chance to win $970 million. I don't know if I'd want to be that person in Maryland, man, that won that last night. I don't know. The more I think about it, it's like the hope is nice, like the thinking about it is nice, but like when it actually happens, I don't know.
It gets taxed like 70% though.
Well, you would, if you take the lump sum and then with the taxes, you get just under half. So like if you would win 100 million, you'd probably get like 44 million or something like that. I bet you lose like 55, 56. I don't know the exact answer. I don't know if it's all the way up to 7. But regardless, I don't know if I would want all that money.
Don't like most lottery winners die.
I don't know about die. Maybe go.
They go broke. Yeah.
Yeah.
My dad said if he wins the lottery, he's gonna get a fountain soda thing in his house, and that's it. He's gonna keep the rest of it.
Yeah. See, part of me is like worried. Like I would be worried, but the other part of me is like I'm so basic, and I enjoy it. I don't think I would make drastic changes. Like I wouldn't.
One big thing and then just.
Yeah, I'd probably update my car. I've had my car for, I don't know, 13 years. I'd probably get like a newer car, not like brand new. I'd probably get like a 2016. I'm not gonna buy a brand new car.
Why not?
I don't know.
Just like a
It's just not who I
regular
am.
car.
I don't know. So part of me would be worried, and part of me is like, I think I'd be fine. My wife, on the other hand, I like she'd spend some money. She's the spender of the family, so she doesn't like when I go to like Target with her because then I judge every purchase. But if I'm not there, then it's like, get everything. All right. So parametric warm-up. Your calculator is going to do most of the work. You just have to know those formulas and be careful entering all the stuff. I'm going to pull this down, and I'm not going to talk a ton about it, but you can kind of score yourself with these problems. So make sure, since you are using your calculator, just make sure whatever you're putting in the calculator, you're writing down on the paper. Because if on number 1, on A, if you only had the answer, they call that a bald answer, and you wouldn't even get any credit if you didn't have at least what you entered in there. So there is A. The speed is 2.912. For B, so make sure you know arctangent is tangent inverse in the calculator, not 1 over tangent, as we found out. Stephen entered 1 over tangent of t over 1 plus t. That's cotangent, and his calculator broke. It wouldn't do it. He was waiting for like 30 seconds. So, and then it said, what did it say? Like overflow error. It said, no,
what was it? It didn't say overflow.
no, it didn't. I've seen that before. What did it say? I forget what it said. It was something like overflow.
Yeah.
Oh,
It's smaller.
it's like right there. No, and do it again.
Okay.
Because I'm just gonna be
Oh,
bugged.
it's a
on
tolerance.
tolerance.
Oh, yeah.
Yes, yes. How'd you know?
I was listening.
Oh, okay. You just knew. Calculator speed. C is the whole final value problem. If you're looking for the position at 4, you know the position at 0, and you know the derivative of the x position. So you're integrating x prime from 0 to 4, and they give you x prime. I don't know. If you guys tell me if you have questions. I don't have a lot to say. D, yeah, go ahead.
So, on that one, I actually did X and Y. I found the new location. I would still get full credit.
I think they give you full credit.
I did that as well.
Yeah, especially I would make sure you labeled what X04 is.
Yeah.
But then if you found more, they'd give you credit.
Okay.
Yeah, you'd be fine. D is kind of the reason why I picked this problem. Not so much for A, B, and C, a little bit to remind you guys of the formulas, but D to remind you guys what your calculator can do. I honestly, I know I showed you guys how to switch to parametric and polar modes in your calculator, but when you guys are graphing stuff and doing math 8 and math 9, I don't think you'll ever be in parametric or polar mode. You're going to be in function mode. The only time that I would ever be in those modes, first of all, I would probably never go to parametric mode. Personally, I never have. I'm not that curious if my answers are right and to verify. Polar mode sometimes, we'll talk about that today when you're looking for the limits of integration, but I barely even do that. So I would stick to function. So for the slope being 2, they're basically saying dy dx is 2. Well, dy dx is dy dt over dx dt. So you get a point for just setting, dy dx equal to 2. Your calculator is going to do it all. You don't have to do what the rubric did. You guys have a couple of options. I would leave it as dy dt over dx dt. And if I was solving it, I would graph that fraction and graph y equals 2 and see where they cross. That would be option 1. Graphing dy dt over dx dt. So the natural log of t squared plus 1 over arctan of whatever. Y equals that and y equals 2 and see where they cross. Your other option is you can subtract the 2 and then find the x-intercept. Like set it equal to 0, graph that and find the x-intercept. Either way, you're using your calculator and the graph to find it. When it says the acceleration vector, since it says the acceleration vector at this point, that tells you they're looking for numeric values. So that would be math 8, I believe. Just push math 8 on both of these to get your acceleration vector at that point. So you're finding the second derivative at each, so math 8 on each of those.
Do you have to label that? Or can you just write like the triangle brackets and then the number? Or do you need to?
I think if you just wrote that, I bet you'd be safe. Yeah. And just make sure we're going to 3 places. Yeah.
So on part B, I did the second part wrong. I got the wrong p-value. But I still did the right process.
Mm-hmm.
So when I get credit for the third part.
What they say is they will, if you make a mistake in your work, they'll read with you so long as you didn't oversimplify the problem. Like if you had gotten t equals 0,
Yeah.
that might make, I know you're still doing the same process, but they might look at that and say, that made the problem too easy. But if you got like 2.849 something.
So basically what I did was instead of finding the intersection that it equals to, I had it solve for the value to.
Uh-huh.
So I got a time of like 2.4.
Yeah, my guess is, and what I would do when I was grading, they would take the person grading your test, they have calculators sitting there too. They would take your t-value and they would check and see if your acceleration vector was right based on your t-value. And they'd give you the point. Yeah. That would be an annoying one to grade. I would like to grade the ones where the averages are like 4 something, point something out of 9. Those are the best ones. Your best averages are like 4 point something out of 9 points. There's some, I've seen some where the averages are like 0.9 out of 9, where they're just tough. I try to, when I pull the FRQ, I mean, you guys have access to all the free response questions over the last however many years, just Google them. But when I pick the ones that we do in the class, I try to stick in the middle range, because what I found is a lot of types of problems get reused. They'll change numbers, they'll change context, and they'll change the questions a little bit, but a lot of them get reused. The ones where the averages are like 0.9 out of 9, those are one-off problems. Like those problems don't show up again. So I try not to focus on those. And then the ones that are like super good, it's like, well, you guys should be okay on those anyway. So I try to stick in the middle. That's how I choose. Yeah.
How do they grade problems if you like have your calculator?
I've been told if your calculator's in the wrong mode, you do not get credit for the first point, but then you can earn your credit moving forward. They'll switch their calculator over to degrees and then do all the math in degrees. So they don't just give you no credit, they'll give you some. Yeah. I don't think I've ever had that happen to a student. After the test, if you checked your calculator and you're like, oh, fudge. Only I didn't say fudge. That's never happened. Plus, it's not going to really affect you that much because, well, I guess the multiple choice it could. The only time that mode affects you is if there's trig involved and you're using your calculator. So, I mean, it might affect you on just a few problems.
But I feel like if you're on multiple choice, you figured out pretty quick. You're in the wrong
Yeah,
place.
because I don't think they're not that cruel where they put the degree option as one of the choices. I don't think they do that because that'd be mean.
That would be me.
And I don't think they do that. So, all right. How was the homework on the polar stuff? I don't even know. A lot of trig. One thing I don't know if this popped up in the homework. I made a note to myself on last lesson and I forgot to talk about it. I don't know if, like I said, I don't know if it came up in the homework, but if ever the question is talking about dr, d theta, I don't know if this came up on the homework, but if this turns out to be a positive number, that means the radius is growing. They'll use phrases like, is the particle moving towards the origin or away from the origin? That can come up on AP questions. And so if dr d theta is positive, that doesn't mean the thing's going to the right. Like normal, normally if a derivative is positive, it's moving to the right or moving up. With polars, if dr d theta is positive, that means it's the particle at that time or at that theta value is moving away from the origin. The distance between the origin and the particle is increasing, is what's happening. And so if your dr d theta was negative, that would mean your particle is now moving towards the origin. Does that make sense? I meant to just say that last time and I forgot. It didn't come up in the notes. Yeah.
Maybe 71.
Yeah, I hope so. We're gonna find out. What page was this on?
739.
739. So far back in the book.
Yeah, this was like on the last lesson.
What'd you say, 71?
Yeah.
Find the points of horizontal tangency, if any, to the polar curve. Is that what you said? Okay. Oh, man. Do you have the right derivative before I start? Or does anybody before I do all this stuff?
Which one was it?
71 says R is 2 cosecant theta.
Oh, yeah, before I even differentiate that, I just multiplied by sine because it got rid of the cosecant.
Oh.
Oh, that's
That
smart.
was a really,
I did.
that made it a lot easier.
Oh,
I did
probably
2
just-
over sine theta.
Because I get the whole thing, I think I just got messed up on.
Because if you multiply it by sine, it just goes to 2 plus 3 sine theta, and then the derivative is just -3 cosine theta, that's it. And then set it equal to 0.
Wouldn't you have to multiply the left side by sine?
Yeah,
Yeah, I got the right answer, so,
It's because it's R times,
Oh, because it's R sine theta.
yeah,
Because you're doing dy. Oh, that's smart.
big brain that
Oh,
one.
I'll see on the last part.
yeah.
He's saying, so the y coordinate is R sine theta. And so if R is this, if you would multiply both sides of this by sine, so R, I guess I should put theta in there. So R sine theta, are you saying this would end up being 2 plus 3 sine theta?
Yeah.
And so R sine theta is equal to 3 plus sine theta. So you could replace that. How smart.
Big brain.
I would never have thought of that.
That's the first thing I thought of.
And then you don't even have to do product rule.
Yeah, that's why I did it.
Because then dy d theta would just be 3 cosine theta.
This is like half a
And then
page.
you just find when that equals 0.
Yeah, that was,
Wow.
yeah, I was pretty happy with that one, not gonna lie.
You thought of that on your own?
Yeah.
Yeah, in the workout solutions, it goes from like, it gets the derivative, and then all of a sudden it just got the answer, like no simplification, there's like
Yeah.
one random line.
Don't you love that? They're like, I don't want to do all that. Hey, there it is.
In the test, we wouldn't have to simplify it once we got to essentially the answer, right?
Well, you're trying to figure out where dy d theta is 0. So there would be some work to do.
We have to do one.
Yeah. That saved a lot of time.
Yeah.
Yeah. I'll do that.
Good for you. All right. Well, today's lesson, hopefully you had a chance to watch those videos. If not, it's not the end of the world. Maybe after the lesson, if you're like, I'm still lost, then maybe watch the videos. But I don't know. Anyway, watch them and think that it made somewhat sense. Did it help? Okay. So that's the hope. All right. We have 2 lessons left. So before I forget, we do have 2 lessons left. We have today, and then we have what I think is the easiest lesson in the chapter, next lesson, called Euler's method. It's basically doing tangent line approximations, but multiple times in a problem, like a few different times in a problem. So I think it's pretty nice, which means we do have a test coming up. So Monday, we are doing that lesson, and then Wednesday for e-learning is your review. I'll have some review guide with worked out solutions for you guys. And your test will be Friday/Tuesday. So you guys in here are testing next Friday. You guys at home are testing the following Tuesday.
And the physics test.
And the physics test.
I'm testing in algebra 2 those same 2 days too. It's gonna be easy days for me. I love test
It's
days.
in one.
You do with the last one on purpose.
Oh, no, yeah. it's in one, and then,
I really don't.
maybe one of them we- Oh, yes.
It's been every single
one.
test so
So we
far.
had one.
It just so happens that like math and probably science chapters are all kind of like 6 lessons long, I would think. And so it just so happens the tests fall around the same time. You're not gonna have chapters that are 10 lessons long. That's too much in a chapter. They're not gonna be 4 lessons long because that's too short. So, yeah, that makes sense.
Just the back-to-back classes. Or,
Yeah.
still brain dead going to
Which one's first? Which test is first?
Here.
Nice.
Yeah.
Aren't the AP tests like the days?
The AP Physics C is May 3rd, and then this one's May 4th.
Yeah.
Well,
But then they're done.
Nope, I still have more.
Well, I'm saying like those 2 are
Yeah.
done.
Yeah.
I feel like
Yeah, chemistry
is
is
really
bad.
good.
I wish after AP testing that you wouldn't have to come back for those blocks.
I think
Yeah,
they
would
go
that be
through
nice?
administration.
We are trying. I-
Especially this year.
Well, that's what I'm saying. In future years and in past years, it couldn't be done because the state has laws of seat time and you have to be here. This year, there are some leniencies. I don't see it happening, but it is on the table. Like we're trying to talk to them about it.
I
At
would
least.
literally only have to come
So,
on Black Days.
That's fine.
I have 7 blocks.
Yeah, block days, first block.
because what they're going to come back, administration going to come back and they're going to say you can still do some teaching, enriching. Like there's
Yeah,
still,
But we can do e-learning.
yeah. I'm just saying I don't see it happening, but it is on the table for discussion. So don't get your hopes up because I don't see it. But.
I don't want to come back.
And then I'm wondering if like other teachers would get mad or jealous because I have like 3 AP classes and so I would have half the workload.
Well, that's their own fault, they should teach an AP.
Well, you don't get to pick what you
That
teach.
sounds like a personal problem.
I didn't graduate college and say, I want AP calculus, please. Like it doesn't work that
You
way.
graduated college and you're able to.
You have
teach
to-
an AP.
You have to work your way up.
How does
Where'd you
teaching
start
classes
at?
get
Where'd you
assigned?
start at math 4?
I started with algebra 1 and geometry. And so I taught those classes for 4 years and only those classes. And then our honors algebra 2 teacher was retiring. And they came up to me and said, would you want to teach, I was at the freshman campus. They said, would you want to teach honors algebra 2? And I said, well, I've never taught regular algebra 2. And they said, that's fine. So I did it. And then I taught algebra repeats. And then I came here to the main campus building. The freshman campus closed. And then our other this was the best. So then our other honors algebra 2 teacher, because I was me at the freshman campus, so I had only freshmen. And then the other teacher over here taught sophomores and juniors in honors algebra 2. Well, when I came over here, that teacher retired and I wasn't teaching calculus yet. So I got all the honors algebra 2 sections. So I had 5 of them and it was awesome because I love that class. And I had a geometry. And then the next year they said, our AP Calc teacher was retiring. And they said, would you want to teach AP Calculus? I said, I've never taught pre-calculus. Does that matter? And they said, nah. I said, okay. So I did it.
But like, how many teachers that are here can also teach calculus? Like, I think calculus teachers are hard to find because we had one retire my old one, we couldn't get anyone to teach it.
Any math teacher should be able to teach calculus. I didn't know any calculus when they came up to me and said, do you want to teach AP Calculus? The only thing I remembered from calculus was the derivative of sine is cosine. That was it. And then the power rule. I knew the derivative of 3x squared was 6x. I knew those 2 things.
So you don't have a degree in math?
Yeah. But once you're done with calculus, like I was done with calculus my freshman year, you don't do, like I didn't use calculus past that.
Yeah.
Like I had other math classes. I had discrete 1, discrete 2, linear algebra, modern algebra, just other differential equations. I had complex variables. You have other math classes that you're not using calculus in a lot. So
it's not just like calculus, but getting more and more difficult.
no. In fact, Calc 2 is the hardest of the calculi. And Calc 3, from what I remember, it's been a very long time. It's been like 18 years. But Calc 3 was just Calc 1, but in the 3rd dimension. Like you get into the z-axis a lot. I remember that. But I remember that being a lot easier than Calc 2. Anyway, okay. So today's lesson is about finding area within polar regions. And if you remember when we first started finding area under a curve, before we even learned definite integration, we did Riemann sums. Yeah, I started recording at the very beginning so he could listen to kind of going over the whatever. And he could fast forward, you know, he could fast forward.
There's fun in that.
But I guess, how does he know when to like play? Whatever, they'll figure it out. So we did Riemann sums where you put in rectangles, then you find the area of those rectangles, add those up, and you say that's an approximation of the area under the curve. Well, it's the same principle when we are doing area for polars, but with polars, we're talking about rotations. And so what we're doing is we are fitting in little sectors of circles. So instead of putting in rectangles, bless you, we're finding areas of sectors of circles. We are making those sectors infinitely small. We're finding the area of every one of those infinitely small sectors, and then we're adding them up. But we're not actually doing that. What we need to know, and the only thing we really need to know is where this formula comes from, is what the area of a sector of a circle is. And it's this formula right here. This is how you find the area of a sector of a circle. It's 1/2 radius squared theta. What that leads to is definite integration. And the area formula for us, our area formula is this, but we just apply a definite integral. So I'm going to pull the 1/2 out in front of the integral times the integral. Now I'm going to label these. I think they use alpha and beta. I'm just going to use A and B because I don't know how to draw those symbols. But I think when they're talking about rotations, they put alpha and beta as your limits of integration. And then inside, it's going to be r squared d theta. Well, r is just f of theta. R is some function in terms of theta. Like they'll write r equals sine of 2 theta. So I'm just going to write this as f of theta squared. This is our formula. It's not a very difficult formula. But again, what this is us finding the area of infinitely small sectors and adding them all up. That's what definite integration is. That's what definite integration is in the Cartesian coordinate plane. Definite integration is finding the area of infinitely many rectangles and adding them up. So in my opinion, the hardest thing of today's lesson is finding the limits of integration, which is what those videos were hopefully helpful about. So here's what I learned that I said is going to be helpful for us. I learned this, I don't know, yesterday or 2 days ago. So what's going to be happening, since R is always going to be some trig function and we're squaring R, we technically in our integrals are always going to get to some trig function squared, like cosine squared theta, and we don't know how to integrate that. We don't have means of integrating sine squared theta. So I, in the past years, have used these power reducing trig formulas. I think you learned these in pre-cal. And so I've done this on the notes. Come to find out, you don't need, they're not going to have you do that. I learned this the other day. The guy said, you won't have to know any trig manipulation. You don't need to know any power reducing formulas. Like, you don't have to have these things memorized. So I might do the first one by using it, because when you get to college, you may still have to do this stuff, but you won't have to memorize these. All right. So cosine squared theta, if we want to reduce this, this is the same as 1 plus cosine 2 theta divided by 2. Did you guys learn this last year? Did you do these? You did not?
This one, I remember the 2 sine theta, cosine theta,
Yeah.
but I don't remember cosine. All that we learned about was cosine squared is equal to sine squared minus 1.
Ah,
Yeah.
okay. Well, that's the good news is you're not going to have to know these anyway. So, but since I just learned it, I didn't have time to take it out of the notes. So here we are.
So you said that we won't have to do any trig manipulations, like to an extent. So with what we did last night, question 71, and like Stephen's crazy sign thing,
Yeah.
would we ever have to do any of that on the AP?
I mean, you could do it to help yourself out, but there shouldn't be a problem where you have to do the trig manipulations.
Okay.
Where like that's the only way of going about it. 2 sine theta cosine theta is sine 2 theta. And the reason this one's important is because if I would put, let's say we were trying to integrate this. Could you integrate this? Why would we have to know this one?
The sine goes to cosine.
U is sine, du is cosine. Yeah, I don't know. Whatever. You're not gonna have to memorize these anymore. Okay. So the first one says, find the area enclosed by one petal of the rose curve R equals 4 cosine 3 theta. When they told me I was going to teach this class, well, they didn't tell me. I asked to teach this class. I actually asked. When I started looking at this stuff and I got to polars, I'd never learned polars at all in pre-cal calculus. I don't remember in college. And I got to this section, and my biggest fear was that I was going to have to know what all these polar graphs looked like all those graphs I put up on the Elmo last time where, you know, they had loops inside of loops and a bunch of rose petals. Like I was like, oh no, you don't have to know those. So typically the graph will be given. If not, you can use a calculator to graph it. That should be pretty rare to do. I've looked back at a lot of the FRQs in the last 10 years. The graphs are always given. Which is nice. So I'm going to give this to you. Here's what the graph of this looks like. I'm not good at this, so just bear with me. Looks something like this. Are you laughing? And that, something like that. It's like a fish. I'm gonna use a pencil for these. So this question is saying, find the area enclosed by one petal of the rose curve. They're basically saying, find the area of like one of these, and they're all symmetrical. When we're dealing with polars, I mentioned this last time, symmetry is everywhere. So if you think something is symmetrical, it is symmetrical. You don't have to like wonder if it is or hope that it is. It's going to be symmetrical. Grab the pencil without erasing. Okay, so here's the thing. A lot of times you're going to be using the symmetry And I would encourage you, in most of the problems we do, just find the area of whatever is in the first quadrant. And use symmetry and multiplication and stuff to get to your final answer. But I would encourage you to try to just find the area of whatever the thing is in quadrant 1. I think that's the easiest when we're finding our limits of integration, okay? So our area formula, I'm gonna write this again. Our area formula is 1/2 the integral from a to b of r squared. So in this case, 4 cosine 3 theta squared d theta. But we're not going to do this one by hand. I've done it in the past. We're just going to do math 9. So I'm not going to focus on the integration. Depending on what your limits are, that's going to find you the area of certain parts of this. So here's the thing. If I only want to find the area of this part right here, let's say I want to focus on this. I want to find the area of this region right here in quadrant 1. We're going to ignore everything else. I want to find my theta values. All right, my limits of integration. Now, here are some tips that I kind of use when I'm finding my limits of integration. Typically, your limits, I can't say always, but pretty much your limits of integration, they're either going to give them to you on the AP test if they're weird values, or they're going to be your basic unit circle values. It's going to be 0, pi over 6, pi over 4, pi over 3, and pi over 2 in quadrant 1. If there's something weird, they're going to give you those values, okay? So, at first glance, when I started doing these, I was like, man, I'm struggling to find these. But when you have that in your mind that it's just those basic trig values, it starts to make more sense. Now, here's the first thing that can happen. We're trying to think, if my graph starts on the x-axis, I'm trying to think of my limits of integration as like rotation values, okay? The first rotation, if your thing starts out here on the x-axis, your first theta value is 0. My first theta value is 0 right here. Then I'm trying to integrate to, notice how this graph enters, they call this the pole. The pole is the origin on a polar coordinate plane. Notice how this graph enters the pole, like right here. And imagine drawing a tangent line right at where that curve hits the origin. So right here, whatever this theta value is, that rotation, that's going to be my upper limit of integration. So basically I'm integrating from out to this first point here and then up to wherever this graph is entering the pole. And I have to find that. That's what I'm after. I need to find that theta value. Well, if that theta value, think of it, that what is that radius value right here? It's 0. So I'm basically trying to figure out what is that theta value when the radius is 0. That's the question. Like right when that curve is hitting the origin, the radius is 0, and I'm after that theta value right then and there. So what I'm going to do, I'm going to go to my R equation. I'm going to set R equal to 0. This is pretty common to find your limits of integration, setting your radius equal to 0. So that's what I'm going to do over here. I'm going to divide by 4. And then what I'm after is the very first time that this equals 0. So now I try to think, okay, cosine of what is 0? You guys tell me, cosine of what is 0? Huh? Pi over 2. The very first one's pi over 2. So I need to figure out what makes 3 theta be pi over 2. Well, you spoiled it, but so to get that, yes. I would set the thing inside the trig function equal to pi over 2, and yeah, theta is pi over 6. So for this particular problem, I am integrating from 0 to pi over 6. Now that is going to find me this region here, but I want the area of that whole thing, so I'm going to double it. So bear with me for a second. Don't write this. I want to explain this. So if I just did 1/2 the integral from 0 to pi over 6 of, I'm just going to write r squared for now. If I just wrote this, if I'm doing from 0 to pi over 6, I'm just finding the area of this shaded region, but I want to double that to get my answer. So I would multiply that integral by 2. Okay, we're using a lot of symmetry. If you're doing pre-response questions, there are multiple integrals that you could set up to get to the right answer. It's important to understand symmetry, especially when you get to multiple choice questions, because they force you to use the symmetry in the multiple choice questions. Like you have to know what's happening there. So we'll practice that on the next one. Like I said, we're just going to do math 9. I'm not going to integrate this by hand. You end up getting 4 pi over 3. I'll show the work here and kind of where that that power reduction comes into play. This is what I always thought you guys were going to have to do. So cosine squared of 3 theta, I squared the 4 and pulled that 16 out in front. But cosine squared of 3 theta, we can't integrate that. So to integrate cosine squared, we break it down to 1 plus cosine 2 theta over 2, which is what this is. What did I do from there?
You took out the 1/2.
Oh yeah, I took the 1/2 out in front. And then we can integrate this with like u substitution. But that, like I said, that's the thing you guys aren't gonna have to do. So it's kind of nice. Some tips with finding your limits before we move on to the next one. So here's kind of how I go about these and what happens in my head. I do that. I set r equal to 0. But if I have like a coordinate plane, your graph is either going to start here like this one did, just like this. It's going to start here. Like if you would graph this in the calculator in polar mode, you would see it start right here. And then you would watch, you could see it graph kind of like this. If that happens, your lower limit of integration is going to be 0 right out here. The other things that could happen that I look for is sometimes your graph is going to leave the pole, the origin, and it's going to go like this. It's going to come kind of straight out. And then it might do something like this. When that happens, when it looks like it's leaving and like tangent to the x-axis, your limit is probably going to be 0 again. I would still set r equal to 0 to verify that, but this is what goes through my head. When I see this, I'm like, okay, the lower limit is probably 0 because it looks like it's leaving horizontally and then coming up. And then it looks like it's coming in basically vertical. So I would probably be integrating from 0 to pi over 2. That's what goes through my head. I would still set r equal to 0 to find that out, to verify, but that's how I look ahead. What else can happen is this. Your graph might do this. Maybe it leaves the pole and it doesn't start out horizontal, but maybe it goes like this. And then I'm just going to, whatever. The rest of the stuff doesn't matter. But notice on, I wish I didn't do that. I screwed that up. But notice how this one's not like leaving horizontally. It's leaving at a different angle. And in my mind, I'm like, okay, if I'm using unit circle values and I'm thinking about pi over 6, pi over 4, pi over 3, this looks like that's leaving at an angle of like pi over 6, the very first one. And it would probably turn out to be that. So I kind of look ahead at what angle is it leaving, at what angle is it coming in, and things like that. Does that make sense? Yeah.
So the question says find the area of one petal
Uh-huh.
on the rose curve. So in rose curve, are they all equal?
Yeah.
Okay.
Mm-hmm.
So it wouldn't matter. I mean, one probably.
They're all going to be, anything that looks symmetrical, it's going to be symmetrical. Yeah. Yep. Okay. You guys try example 2. Multiple choice question. Kind of hard to see, but all the limits say 0 to pi. All right. I got D. So if this was me doing this problem and it wasn't multiple choice, well, first thing I notice is it looks like it's kind of leaving horizontally. So it's the first lower limit is probably 0. I'd probably set R equal to 0 to verify that. And if you do, you find 0. I would probably integrate from 0 to pi over 2 and just find the area of that little half moon right there. That's what I would do if it was a free response question. Since it's multiple choice, they're not giving you that option. They're having you integrate from 0 to pi. So they're having you integrate from the starting point and then all the way over to pi over here, which means, let's see, what's this asking us to find? The area of the whole thing? The total area, yeah. So if you are doing from 0 to pi, think about if I was finding from 0 to pi of 1/2 of sine squared theta squared. So sine to the 4th theta d theta. If I just did this, think about what this finds for you. This formula, which is the formula that I talked about, finds from 0 to pi, that finds this right here, which means we would then need to double that to get the area that we want, which is why the answer is D and doesn't have the 1/2 out in front. So you need to pay attention with that 1/2 and the doubling and the symmetry. Just take your time on these. Yeah.
Why would you do the pi over 2?
Because for me, I know 100% that's pi over 2.
Okay.
And that I just like dealing in the first quadrant. It's just easier for how I think. I don't know. Yeah. All right. The next thing that can happen is they might put 2 polar curves on the same coordinate plane. So if you watch those videos, this is what the second one was about, when you have polar functions that are intersecting. So this question says, find the area inside 4 sine theta, which is this top one, and outside r equals 2. R equals 2 is the circle right here. It means it has a circle of radius 2. So that's how I know this one is r equals 2, and the top one is 4 sine theta. It wants the area inside the top one, but outside the bottom one. Basically, it wants this area right here. So if we want to find the area between 2 polar curves, imagine finding the area of like this whole region, the whole thing, and then taking away the area of this stuff that you don't want. Kind of like in geometry, you'd find the area of the whole thing, take away the area of what you don't want. That leads to this formula. It's going to be 1/2, and then from A to B of R2 squared. So the big one, that's finding the area of like the whole region. And then you want to take away the area of the missing stuff. Another way you can write this, I mean, this to me conceptually makes the most sense. But another way you can write it is you could pull the 1/2s out, integrate from A to B, and just do r squared minus r squared. However you want to think about it, but it's doing the same thing. So the only difference when you have 2 polar functions, you might have to find where they intersect. Because on this particular one, okay, if it's me doing this problem, and it is because I'm the one doing the problem, I'm integrating from here. Imagine that, whatever that theta value is, out to there. And then I would probably go up to pi over 2. That's me. You could go from this first intersection point and then to the second one. That'd be fine. But there's multiple ways to do these problems. Okay. All right. So however you are going to do it, but the first thing we need to figure out is what is this theta value right here? Now to me, I'm like, okay, it's probably going to be one of my unit circle values which means it's probably going to be pi over 6, pi over 4, pi over 3. It doesn't look like it's the 45-degree mark, so it's probably not pi over 4, which means it's probably pi over 6. I just think through that ahead of time. But to find it, well, I just set my two things equal to each other. I find the intersection. So 4 sine theta equals 2. And then I solve this. So sine of theta is 1/2. And then I just try to think, where is sine 1/2? And that's at pi over 6. And the other place is 5 pi over 6. So if you wanted to do it to 5 pi over 6, that's up to you. So when I'm doing my problem now, it's going to be 1/2 the integral. I'm just going to do it from pi over 6 to pi over 2. Which means I'm just going to be finding this area here in quadrant 1. So then I would double it and put that 2 out in front. So the 1/2 is going to be gone. If you would want to do from pi over 6 to 5 pi over 6, you can, and then you would keep the 1/2 out in front because you wouldn't be doubling anything. You would be finding the area that you want. So it's completely up to you if you want to use the symmetry or you don't. For me, just to take a lot of the thinking out of the equation, I'm always like, I'm going to try to do it in first quadrant if I can. But again, that's me. And then inside, it's going to be the big function squared. So 4 sine theta squared. So 16 sine squared theta. Minus the inside function squared. So minus 4. And so since you're not going to have to be using these power reducing formulas, these things are either going to be set up the integral and don't evaluate or use your calculator. And it's 7.653. You guys think of these? Like them? Fun? Fun? Woo! Just energized me. Wasn't expecting that. All right. Do it. Example 4. Kind of like the last thing that I can teach you with these. Find the area of the inner loop of r equals 2 minus 4 sine theta. So this graph, when it says inner loop, here's what this graph looks like. I think it's called a limacon. I don't know. I could be wrong. Something's called a limacon. But it looks like this. It starts here on the x-axis. It curves in like this. Does this little loop-de-loop. Comes back out here. And then does a big loop. It's actually not too bad. That's what this graph looks like. So it wants us to find the area of this inner loop right here, inside here. So it's important to understand kind of where the graph starts. This is where you might graph this in your calculator to see where it starts, because the graph does start right here. And since I only want the area of the inside loop, I don't really care about this starting point. I want to think, when does that inner loop get started? Like the particle, if I was graphing, goes like this. It starts here on the x-axis, and then it's going to trace until it gets to right here. This right here is when that inner loop gets started, when the graph goes like this, and as soon as it gets here. So I'm after this theta value right here. That theta value, whatever it is. Now I graphed this terribly, so I'm not going to eyeball this one. I don't know exactly what this one looked like. But whatever that theta value is, that's going to be my lower limit of integration. And now I have some options. I can integrate from whatever that theta value is, which we're going to find by setting r equal to 0, because right there at the origin, r is 0. I can integrate from that theta value to right here, which is 3 pi over 2, and then double it. Or we can figure out, okay, the particle's moving along this inner loop until it gets to here, and then we can integrate to whatever that theta value is and not have to double it. You have the choice. So I need to find those theta values. So right here, when r is 0, let's see what we get. So subtract 2, divide by -4. So sine of theta is 1/2. Hey, we just did that one. So theta is going to be pi over 6 and 5 pi over 6. Again, your two options, you can integrate from pi over 6 to 5 pi over 6, in which case you would leave the 1/2 out in front. Or you can integrate from pi over 6 to 3 pi over 2. But that would just be finding the area of the left half of that inner loop. And so you'd have to double that value and the 1/2 would go away. I stress talking about both because with multiple choice, you are going to have to understand based on the limits they give you, are they using symmetry and things like that. And then I would just push math 9. I don't know what the answer is. I didn't write that one down. Looks like it's 3 point something. Just made that up.
And these are also symmetrical, right?
Mhm. Yeah, there's symmetry everywhere. Symmetry. All right. I want you guys to try these two. You can use your calculator. Try these two problems here. See how much you know about polar functions. You need to work it out too. I'm not getting the answer I should be getting. But I get B. Everybody at home get B. An answer for B. No. I feel like I did it right. I have someone else's work. We have the same integral set up, but we have a different answer in the end. For B. I got 28.028. 9.525. We have the same integrals and same limits. Shouldn't, I don't think it should matter. So I'm trying to make sure that I entered everything and like squared it all correctly. Like I'm like 99.1% sure that what I have is right. Five cosine of x, cosine 5 cosine x, all squared. I did from 0. Ah, crap. That 0.9%. Second one, I integrated from 0 to pi over 2 instead of pi over 3 to pi over 2. Gosh dang it. Ah. I did it. So mad at myself. I let the team down. Okay, so on this one, step one is identifying which curve is which. And let's say you didn't have a calculator and you needed to determine which polar function went to which equation. The way I do it is this. I just think, okay, when theta is 0, notice that these graphs are at 2 different places. And I just plug 0 into each equation and see which one's at the right place. Like for instance, for the 5 cosine theta, if I plug 0 in, I get 5. So that tells me when theta is 0 on the R2 graph, I should be at 5, and I am. So that's how that tells me that one's R2. So that's first and foremost. So the first question says, find the area inside the graph of R1. So for part A, ignore R2. Imagine R2 is not even there. R2 is not even in the problem for part A. All it wants us to do is find the area of this graph right here on the left. Depending how you guys set it up. So I know I've said I like to do it in quadrant 1. I looked at this one and I was like, well, if I just integrate from 0 to pi over 2, I'm then again going to have to integrate to get this stuff here from pi over 2 to pi and double that. Like I'd have to do 2 different integrals. So for this particular one, I integrated from 0. And then when I did it to pi, that took me all the way over to here. So me integrating from 0 to pi was finding the top half of whatever this graph is called. And so then I doubled it to get the bottom part as well. So I integrated from 0 to pi of R1 squared, and then I doubled the 1/2. Does that make sense for the first one? Tell me if it doesn't. The second one, so now I have to identify what does it want me to find the area of? It wants the area of the region inside R1, and also inside R2, like a Venn diagram. So it wants this, I shaded it in pencil. It wants this area here. Well, anytime your graphs are intersecting, you're probably going to have to set up multiple integrals. There's nothing to subtract this time. But if I integrate from 0 to pi over 3, because it tells me on this one that's where they intersect. If I integrate from 0 to pi over 3, that's going to find this little chunk here. Then to find this little chunk that I'm missing, I would then integrate from pi over 3 to pi over 2 of R2 squared. Notice this part here from 0 to pi over 3, I'm dealing with R1. So for right here, I did it from 0 to pi over 3 of R1 squared. And I doubled it because that only finds the quadrant 1 portion up here. But then I have to find the area of, like I said, this little region. So I have to integrate from pi over 3. Now, by the eyeball test, it looks like it's coming in to the pole vertically. Like right here, it snuggles up with the y-axis. So that tells me it's probably coming in at pi over 2. But to verify that, I set R2 equal to 0 right here and just verified that it is pi over 2. But you can kind of tell when it's snuggling up with the y-axis or when it leaves and it's snuggling up with the x-axis, it's probably 0 and pi over 2. So this was my screw up. I integrated from 0 to pi over 2, but it should have been from pi over 3 right here to pi over 2. And that only found the top hat, little top part right here. So I had to double that to get the corresponding bottom part.
Would an integral of stuff from pi over 3 to pi over 3 work if you cut the 1/2 or no?
Pi over 3 to 5 pi over 3. I think that would work. Anybody do that?
Yeah.
Did it not work?
I did not. I kept the 1/2 out.
And did it from pi over 3 to 5 pi over 3?
Are you supposed to, I subtracted the two integrals. Are you supposed to add or subtract?
You're adding them.
How do you add them?
Yeah. Because you're not, this problem is different than this one up here. This one up here, we were finding the area outside of one, but inside the other. So we had to find the area of the whole thing and take away the area of the inside part. But this one, we have to add them because the first one finds this area, but then we still want this area. So we're adding it together. So try that and let me know. I'm thinking it should work to go from pi over 3 to 5 pi over 3 and keeping the 1/2 out in front. All right, we're done with polars. You've learned everything about polars. Next class, we have Euler's method. Review, test. I do have the group review guide, I think, on today's Canvas page. If you guys want to work with the group and get 2% added to your test, I have that on today's page. That will be due by the time you take your test. And I'll also have a separate review for Wednesday e-learning. A lot of review, practice, practice, practice. Then we get into series. All right, you guys at home, you can leave. Good day. That was a long day. Jam-packed. Calculus.